When people ask, which neural network should I use for a large language model? They often imagine there's a single best answer, like choosing the fastest engine for a car. But LLMs are more like entire vehicle platforms. The neural network architecture is important. Yes, but what matters is whether it fits your job. Writing, chat, classification, search, translation, summarization, or some combination of those. An architecture choice is really a choice about trade-offs. You're balancing quality, latency, cost, and the amount of context you want the model to handle. Some networks are amazing at reading and understanding text, producing stable outputs like embeddings or labels. Others are designed to generate text smoothly, one token at a time, which is what you want for chatbots. Some are built for strict input-to-output transformations, like translation or controlled rewriting. And more recently, there are efficiency-focused designs that aim to handle very long contexts or reduce compute. So the best way to approach the question is to start with a practical framing. Do you need open-ended generation, like a chatbot that can write paragraphs and code? Or do you need robust understanding, like ranking documents, classifying support tickets, or extracting facts? The answer to that one decision already narrows the architecture space dramatically. Encoder-only models are the classic readers. Think BERT-style architectures. Their defining feature is that they look at the input bidirectionally, meaning each token can attend to tokens both before and after it. That makes them great at understanding. They form strong representations, embeddings, that capture meaning in a way you can use for search, classification, clustering, ranking, and extraction. If you're building semantic search, an encoder-only network is often the most efficient and stable option. The output is predictable. You get a vector embedding or a score. If you're sorting support tickets by category, detecting sentiment, pulling named entities, or doing any workflow where the model's job is to label or retrieve rather than talk, encoder-only is a strong fit. This is why RAG systems frequently rely on encoder models under the hood. Retrieval is basically an understanding problem. Map text to representations, compare meaning, and pull back the most relevant passages. Encoder-only networks do that well and usually with lower cost per request than a big generator model. But encoder-only models are not natural chatbots. They can be adapted to generate text, but they don't do the core next token generation loop as cleanly as decoder-only models. So if your product experience is conversational, encoder-only is typically a supporting actor. Retrieval, re-ranking, classification, moderation, not the main voice. Decoder-only transformers, GPT style, are the modern writers. These models generate text token by token using causal attention, meaning they only look backward at what's already been generated. This is perfect for chat, long-form writing, coding assistance, brainstorming, and the general talk-to-the-model use case. One reason decoder-only became the default is that it scales extremely well. If you increase training data and model size, performance tends to improve in a broad, general way. A single decoder-only model can be instruction-tuned to behave like many tools: a tutor, a writer, a developer assistant, a summarizer, and more. That flexibility is why chat-based LLM products often start here. The trade-off is that generation is sequential. If you ask for a long answer, you're paying for the model to produce each token in order, and your latency increases with output length. This is especially noticeable in real-time applications. The model's compute isn't just about the prompt, it's also about how many tokens you want it to produce. So if you need a high-quality chatbot, decoder-only is usually your baseline. Then the practical question becomes, how big should it be? And what supporting components do you add so it stays grounded, like RAG retrieval, tools, guardrails, or smaller specialist models for fast classification? Encoder-decoder, or seq-to-seq transformers, combine a reader and a writer. The encoder reads the entire input, building a representation of it, and the decoder generates the output based on that representation. This design is a natural fit when your task is a clear transformation from one text to another. Translation, summarization, rewriting, formatting, and structured text generation. If you're building a product that consistently converts text in a controlled way, Say, turn these meeting notes into a structured report. Seku can be more efficient than a pure decoder-only approach because the architecture matches the task. The model can attend across the full input via the encoder, then generate with the decoder. The trade-off is complexity and sometimes cost. You have two stacks, encoder and decoder. Depending on model size, this can increase compute per request. And if your product needs open-ended chat, the SSXCQ framing can feel less universal because everything is implicitly given this input, output that, rather than maintain a conversation naturally. That's why many teams still default to decoder only for simplicity unless they strongly benefit from this execute structure. But if your app is heavy on transformations and you want more controllable outputs, encoder-decoder is a strong option to keep in your toolkit. Once you choose the basic transformer family, encoder-only, decoder-only, or encoder-decoder, the next question is, how do you make it efficient enough to ship? One important idea is mixture of experts, or MOE. In a dense model, every token goes through all the parameters every time. In an MOE model, a router chooses a subset of expert blocks for each token. The result is that you can dramatically increase model capacity, how much it can know and represent, without paying the full compute cost on every token. You get something like a giant brain where only the relevant parts activate. Another major axis is long context. Standard attention gets expensive as context grows, both in compute and memory. That's why you see long context variants that use sparse attention patterns, windowed attention, caching strategies, and compression techniques to make longer prompts practical. If your product relies on large documents, contracts, manuals, research papers, these efficiency choices matter as much as parameter count. Then there's the simplest efficiency lever, smaller models. A well-tuned smaller model can be excellent for a narrow job. In real products, a common strategy is to use small models for most traffic and only escalate to larger models when needed. And for factual accuracy, small models often pair extremely well with RAG. You let retrieval supply the facts, and the smaller generator focuses on writing a grounded answer. If you're choosing architecture for production, don't ignore these variants. The difference between a demo and a shippable system is often whether your architecture fits your cost and latency budget. Transformers dominate, but they're not the only game in town. There's active work on architectures designed to handle long sequences more efficiently. One family is state space models, or SSMS, which aim for more linear time sequence processing rather than the heavier attention mechanism. The promise is that you can scale context length more gracefully and potentially reduce memory pressure. There are also hybrids that keep some attention, because attention is incredibly powerful at precise context mixing, but replace other parts of the block with more efficient sequence operations. In other words, the industry is exploring mostly transformer ideas that preserve quality while improving speed and context handling. But here's the reality check. Architecture adoption is not just about theoretical performance. Transformers have an enormous ecosystem, training recipes, libraries, inference optimizations, deployment stacks, and community knowledge. Even if a new architecture looks great on paper, it has to compete with the reality that transformers are easy to train, easy to scale, and easy to deploy because the tooling is mature. So if you're building a product today, transformers are usually still the default choice. Alternatives become relevant when you have a very specific constraint, like extremely long context with strict latency, and you have the engineering capacity to adopt newer tooling. So what neural network should you use for LLMs in practice? The simplest map is this. If your experience is chat or open-ended writing, you typically pick a decoder-only transformer. If your job is convert this text into that text with structure and control, encoder-decoder is often a great fit. If your job is understanding search, ranking, classification, extraction, encoder-only is the workhorse. But most real systems don't use just one model. A common production stack looks like this. An encoder-based retriever finds relevant documents, an encoder-based re-ranker improves the quality of those results, and then a decoder-based generator writes the final answer. That's RAG in a nutshell. plus the engineering pieces. Guardrails, evaluation sets, and monitoring. This is the deeper answer to which neural network. You're often choosing a combination. You use the right network for the right role. Readers to retrieve and judge, writers to generate, and efficiency tricks to hit your latency and cost goals. And the direction things are moving is towards specialization. Smaller models for cheap calls, MoE for capacity, long context variants for document-heavy workflows, and hybrids that chase better efficiency. The best architecture for you is the one that ships reliably and meets your product constraints, not the one that wins a single benchmark. Next to real reliability in products, watch my video on retrieval augmented generation next. It's on screen now. And if you found this useful, subscribe for more clear, practical AI explainers.